Hello again. This is the second video in the acidic environment topic, and today I want to look at describing acids and bases. Hopefully you've watched the previous video by now and you've got a little bit of a context set for this. So the last video should have pretty much been revision for you guys. This one may introduce a few new concepts for you, or at least extend some of the ones that we've looked at before in a little bit more detail. So I guess let's get into it. The first thing we want to do is define two very important concepts that I want to look at here, and then to start getting a little bit of an understanding of the relationship between them. The first that we want to look at is the strength of a solution. The strength of a solution refers to the degree of ionization. So when we're talking about acids, we talk about the fact that any acid is going to ionize into the H+ ion, which is going to link with water molecules to form a hydronium ion and an A-. If there are lots of these, then we say it's a very strong acid. If it's mostly still molecular form, then we say it's a weak acid. So the concept here is related very much to how readily a molecule will ionize in water. The concentration, on the other hand, refers to the amount of acid compared to water. Okay, so it's a relative or ratio, if you like, between acid and water. So the acid could be acid molecules, or it could be ions if it readily ionizes. So there can be a strong concentrated acidic solution. We can also have a weak concentrated acidic solution. So it's important that we don't confuse these terms. For those of you who want to, I guess, fill some of the gaps in the workbook, this section on this particular PowerPoint goes from page about 44 through to around about 55. There are some practical activities in there that we will do, obviously, when I come back. So what we want to do then is, when we've got these two concepts of strength and concentration, then we can compare acids and also bases on the basis of the degree of ionization and the relative amounts of water in the solutions. So one of these, okay, the degree of ionization is related to the acid strength. So that's related to strength. And the relative amount of water is related to concentration. And of course, we will come back and have a look at that in a little bit more detail in just a moment. Come on, mouse. Okay, so what does this actually look like? When we are trying to understand how we identify acids and bases, generally speaking, what we talk about with acid solutions is a certain concentration. So here, for example, is a concentration, a 0.1 molar solution, moles per liter. We have three acids here, okay? Hydrochloric acid. Hydrochloric acid, hopefully you'll be aware of, this is a strong acid. One of the reasons we know it's a strong acid is it's 100% degree of ionization. It's fully ionized. There are no HCl molecules remaining in this solution. However, both acetic acid, which we talked about in the last video, and citric acid are weak acids. And you can see there's a difference in the degree of ionization for both of these. 27.5 for acetic, and 4.2 for citric. So that means that if you were to look at each of these solutions with your micro eyes, you could find no molecules in this one. They would all be H+ ions and Cl- ions, whereas in both of these two, the number of H+ ions will be small, and the molecules, and still for the molecules, molecular forms dominate. Okay, so for each of these, the molecular form dominates, particularly for the citric acid. Is there any way we could convert this? Well, there is, and perhaps you might like to have a little go at this. The first one should be fairly straightforward, particularly if we remember that pH is equal to minus log base 10 the concentration of H+ ions. If 100% of the HCl is ionized, that means that because it's a 1-to-1 ratio, that we would have 0.01 molar solution of H+ ions, and therefore the pH will be equal to 2. Stick it in the calculator if you're not sure, but that's what it would be. In the second example, acetic acid is a 1-to-1 ratio as well, but this time only 27.5% of the acid has been ionized. So therefore, even though it's a 1-to-1 ratio, we have to multiply this by 0.275. 0.275, that shouldn't be up. Get rid of that. And so that is going to be equal to something that I will need to check out on my calculator. So sorry for messing around, you've probably already done it now and I'm still trying to figure it out. Where's my calculator? There it is. So 0.01 times 0.275. And why am I doing this when it is as simple as that? So it's effectively going to be 2.73. Let me go down here. 2.75 times 10 to the minus 3. So that's a concentration, and if I put that into the pH formula at the top, 0.0275, I should have a log somewhere, a log base 10. So that's going to be 2.56. So in this case here, pH equals 2.56. Yeah. So you can see the fact that it doesn't fully ionize means that we have a difference even though the concentration of the solutions is the same. The problem that we have for the third one is that in this case we have a 0.01 molar solution, which is going to be multiplied 0.042 because only 4.2% of the solution is ionized. However, citric acid is triprotic, and therefore we will have a 1-to-3 ratio of molecule to hydronium ion. So therefore we're going to have to multiply this by 3. So that's going to give us a value of 0.01 times 0.042 times 3. 1.26 times 10 to the minus 3. So this is 1.26 times 10 to the minus 3. When I put that into the pH equation above, my pH is going to be 2.90. So you can see the difference in the pH for each of these three substances, even though all of them has the same concentration. The degree of ionization is different, and therefore there is a difference in the pH for each of these solutions. I know that's rather messy. I hope you can follow. So then the first thing we want to do is to start to look at acid strength. Now this is this link to this particular interactive is in your booklet, which is also on my house, so you can follow this if you like to have a look. But I will explain this in a little bit of detail as we go along. So the first thing we want to do when we're talking about acid strength is we're talking about degree of ionization. So strong acids are acids which are completely ionized, and we already had a look at an example of that before, hydrochloric acid. So is sulfuric acid. Both of these are very strong acids and they will completely ionize. That's the important thing here. They completely ionize. So we can assume when we're looking at the concentrations of each of these solutions that they're very easy to work out, because you can assume that all of the the concentration of the solution is equivalent to the concentration of the H+ ions for a 1 for a monoprotic acid, as all are the molecules have been ionized. The problem is that weak acids are not completely ionized, and as you just saw from the previous slide, some of those are more ionized than others. And the thing is, unless we have some measuring device, we don't have any idea to what degree each of these is ionized. And you don't need to remember proportions and percentages of those sorts of things, but you should be able to explain the difference between a strong and a weak acid. So when you're looking at weak acids, any of the organic ones that we've looked at so far, so I might just put in acetic acid from the previous slide, CH3COOH, which is acetic acid or ethanoic acid. What this looks like in reality can be seen from this particular image. If you look at this image, in this solution, most of the species in water are molecules of HF, okay, hydrofluoric acid. So you can see most of the molecules have been retained as molecules. There's only one anion here, and there is an H+ here, okay? So I can only see one of those. All of the rest are molecular species. These fellas are a little bit close together here, but they would separate apart from one another. But you can see what happens is that there's a very large number of molecules and a very small number of ions. So this is a weak acid. If we were to look at hydrochloric, on the other hand, how would it differ? The main reason it would differ is because we would have lots and lots of hydrogens and anions and none of these. Okay? It would fully ionize. So as over here we've got lots and lots of molecules and not very many individual ions, HCl would be dominated by these, okay, the individual ions. So if we were to draw a sort of a grid the same way that we had before, the HCl down here would be at 0, H+ would be up here, and because the ratio is 1:1, Cl- would be up here as well. So this would tell you that HCl is a strong acid. The concentration is different. Concentration is not about the degree of ionization at all. Concentration is about the ratio of molecules or ions to water. So a concentrated solution, as we saw before, is one which has a high ratio of the acid or the H+ ions if it fully ionizes to water. Conversely, dilute acids have a low ratio of acid ions to water. How do we actually show each of these? Well, it's difficult to do it without I guess trying to show the water molecules as well. But if I had a certain area which was roughly the same, which these aren't, but you kind of get the idea. And if I was talking about a strong acid, then I would have lots of H+ ions. I don't usually write on a slope, but I am at the moment. And of course, for every one of these, there would be a corresponding anion. And all of these would be in this region of water. Okay, lots and lots of them, all having been ionized. Conversely, in a dilute acid, there would be very few ions. This is if both of these were strong. So they're both readily ionized. If they were both weak, then they would be dominated by the molecular species. But even so, we may still have one of these, maybe one of these, maybe one of these down here. That is dilute. Up here, we would have quite a few of these molecular species, like this, and maybe the odd anion and proton as well, just as a consequence of some. So you can see this shows us that there is a difference between strong and weak in terms of the degree of ionization, and also ratio of acid to water when we're looking at the difference between how many of each there is in a given volume of water. So I do want to just touch on the pH scale a little bit as well, and you can follow that. I gave you a small calculation just beforehand. The pH, most of the information on the pH scale is on pages 48 through to about 51. And there's a worksheet there for you as well if you want to have a go at it on page 50. When you're working through the pH scale, the important thing is this equation here, and it's one of the ones that's going to appear on your HSC datasheet. So it's not important for you to learn it, but I hope by the time you get to your HSC, you've done so many questions that you know it anyway. You won't even have to look it up. The important thing is that the concentration of hydrogen ions should be in moles per litre. And we do know, or we're going to start realizing now, that the H plus is equivalent to the H3O plus. Okay? So we use these two terms interchangeably. The important thing is that when we are moving through the pH scale from a value of, say, 5 to a value of 6, we're only going a single unit in this direction. What we're doing is we're reducing the concentration of H plus ions by a factor of 10. So it's 10 less in this direction, and it's a 10-fold increase in the opposite direction. So therefore, a pH of 5 has a concentration of hydrogen ions that is 10 times the concentration of a solution at a pH of 6. And that's just understanding the difference between a linear scale and a logarithmic scale. Of course, when we're looking at our calculations for pH, sometimes we're given solutions that contain or that liberate hydroxide ions. And if we do know the concentration of hydroxide ions, we can still work out the pH. Firstly, by converting the concentration into a pOH in the same way as we have with the pH formula. And then remembering that there is a relationship between pH and pOH that gives us the value of 14. If you simply remember that water is a neutral solution and there's equal concentrations of hydrogen ions and hydroxide ions, and the pH of water is 7, then if these two things are equal, then 7 plus 7 must equal our magic number of 14. It's not important for you to be able to derive this equation, but it's probably useful for you to remember it nonetheless. So here's a question for you to practice. 20 mils, and this has come out of a past HSC. 20 mils of a 0.08 molar hydrochloric acid solution is mixed with 30 mils of 0.05 molar sodium hydroxide. What's the pH of the resultant solution? Now, one of the important things when you're going through these sorts of questions is you need to remember that not all information that you're given assumes that every reaction goes to completion for all of the quantities that we have. It is possible that one of these substances may be a limiting agent and the other one is in excess. In order for us to determine whether that's the case, we must first of all write the equation. So HCl plus NaOH is going to H2O plus NaCl. Now again, I haven't written the subscripts, but it's important that you do that because it gets messy for me trying to write aqueous. So this is aqueous, this is aqueous, this is liquid, and this is aqueous. The equation is balanced, so therefore my mole ratios is just a coefficient at the front, which, because there isn't one, means they're all ones. And then I have some things I can look at here. I have number of moles, I have volume, and I have concentration. In the first case, I have hydrochloric acid, 0.08 molar. So this is concentration, 0.08 molar. And I have 20 mils, and I'm going to convert that to litres because it's just easier for me to work with. So when I go up, I go N equals CV. So this is 0.02 times 0.08. And you can do that on your calculator. Maybe I'll do it in your head, H is 16, and then you just work out the particular power that you need. Hang on a second, 0.02 times, I'm just going to do it on the calculator because it's easy to make a mistake in my head. So it's 1.6 times 10 to the minus 3. So this is 1.6 times 10 to the minus 3 moles. Okay? We do the same thing here for this one. Concentration is 0.05 and the volume is 0.03 litres. Okay? So when we multiply these things together, we get 0.03 times 0.05, and we're going to get 1.5 times 10 to the minus 3 moles. What you can see is that we have an excess of acid. Okay, this number is greater than that number. Therefore, when this neutralization reaction occurs, the 1.6 times 10 to the minus 3 moles of the acid will react with the 1.5 mole times 10 to the 3 moles of the base, and it will leave an excess of acid, 0.1 times 10 to the minus 3, or 1 times 10 to the minus 4 moles. What I need is a concentration. If I'm going to find the pH, I need the concentration of the H plus ions. In order to find the concentration of the H plus ions, I need to find a concentration, and what I have is a number of moles. So I need the volume. Now the total volume is now 30 plus 20, which is 50 mils. I have to remember that if I'm mixing these together, I have now to take into account the total volume that I have, and that is equal to 0.05 litres. So the concentration is equal to 1 times 10 to the minus 4 on 0.05. Sorry, that's getting really messy. So what we have then is a 0.002 molar concentration of H plus ions, and then using my pH formula, minus the log of 0.02, and that gives me 2.70. So my pH is 2.70. Double check that, make sure you can get to the same result, and if you can't, maybe check my math and make sure I haven't made any mistakes if you can read that. So one more activity for you to complete the lesson, and once you finish this table, then I have collected some of the books, as you can see, but not all of them. So please make sure that you get up to date. You should be able to be pretty close to being finished on the third section from the booklet. But what I want you to do is to use your textbook. Now you can use pages 160, where are we? Pages 162 to 163 of your Jacaranda textbook, where you'll find information about each of these different types of acids. Okay, all of these are acids that are used as food additives for different reasons. So what I want you to do is to identify whether they're monoprotic, whether they're diprotic, or triprotic, or maybe something else. And I've identified for you the first one, citric acid, because we've done this one before, is a triprotic acid. So therefore, per mole of the acid, we will liberate 3 H plus ions. Citric acid is found in citrus fruits and some vegetables, and it's used as a flavoring and a preservative. So have a go at that. Have a look at pages 162 to 163, in your book and see if you can complete the table. And I'll see you on Tuesday. All the best.